This video will cover a history of supersonic travel as well as the physics behind forces acting on planes traveling at supersonic speeds and how to measure the speed of sound at different mediums. First, we must understand what sound is and how it travels. Sound needs a medium to travel in and moves in waves with the high pressure and low pressure zones being the peaks and troughs on sinusoidal graphs. The speed at which these pressure waves move outwards from the object creating them is known as the speed of sound. Sound travels at different speeds depending on the medium, and the speed at which it travels depends on a number of factors. The speed of sound in any medium is represented by the formula V equals the square root of B over rho, where B is the bulk modulus, also known as the coefficient of stiffness. The coefficient of stiffness measures how stiff a material is or how difficult it is to compress. The stiffer the material, the larger the value of bulk modulus. Rho is the measure of the density of the material. The larger the density, the higher the rho value, and the lower the speed at which sound travels through the medium. The larger the bulk modulus of the material, the faster the sound travels through it. Let's use copper as an example. The bulk modulus of copper is 1.17 times 10 to the 11 pascals, and the density of copper is 8,940 kilograms per meters cubed. Therefore, the speed of sound in copper is 3,618 meters per second. The speed of sound in copper is about 11 times the speed of sound in air, meaning that if you put your ear against a copper roof and hit it with a hammer, you would hear it with your ear against the metal 11 times sooner than you would hear it with your ear not against the metal. The speed of sound in air depends on the temperature and can be represented with this equation, where C is the speed of sound in meters per second and T is the temperature in Celsius. Sound travels at faster speeds when the temperature is higher. This makes sense as the particles are colliding faster when they have a higher kinetic energy. One way to test the speed of sound in air is to perform the following experiment. First, use Google Maps to measure a flat, uninterrupted local distance of around 500 meters in a straight line. Record the exact result. Go to that measured location and have one student stand at the end of the 0.5 kilometer line and the other student at the other end. Record the temperature outside. Next, have student A use their camera to film student B half a kilometer away honking a car horn or air horn and record the exact amount of time it takes for the sound to reach student A after the horn is pressed. As a visual aid of when the horn is pressed, throw a towel in the air when you are pressing the horn. The speed of sound is the distance covered divided by the amount of time that it takes. The time it takes light to travel this distance is around 1.5 times 10 to the negative 6 seconds, so it is disregarded as it is so negligible. We can do these calculations to calculate the predicted speed of sound at the temperature recorded and compare it to our recorded result with the correct number of significant figures. Here's a video of the experiment. As you can see, there is a delay between the towel being thrown in the air and the sound of the car horn reaching the camera. Let's play that part of the clip now. That time it took for the sound to travel from the horn to the camera was 1.3 seconds, which is the same as our calculated time, so our calculations are correct. To understand the importance of supersonic flight in human history, we must look back to the first times humans traveled at supersonic speeds. In 1935, the term sound barrier implied a physical wall that could not be broken by humans. Cannons, bullets, and whips had been breaking the sound barrier for thousands of years, yet no one knew whether a human or aircraft could withstand the forces that accompanied traveling at such a high velocity. After World War II, a special aircraft was designed known as the Bell X-1, and an elite group of pilots was trained to accomplish this task. The plane was powered by a liquid-fueled rocket engine and was dropped from a B-29 bomber once it reached cruising altitude to save on fuel. On October 14, 1947, American test pilot Chuck Yeager became the first person to break the sound barrier. To understand more about supersonic travel, a few terms must be defined: Mach, G-force, what a sonic boom is, and what is the sound barrier. Mach is defined by the speed of sound in a given medium and is represented by the formula m equals v divided by c, where m is the Mach value, v is the velocity of the object, and c is the speed of sound in a medium. For example, the speed of sound in air at 0 degrees Celsius is 331.5 meters per second, and if the speed that you are traveling is 400 meters per second, the speed at which you are traveling is Mach 1.207, as represented with this equation. Secondly, g-forces are a unit of measurement used for calculating the force of acceleration felt by an object. 1 g is an acceleration of 9.8 meters per second squared, which is the acceleration of gravity. Therefore, an object with an acceleration of 29.4 meters per second squared would have an acceleration of 3 g's.
A formula to represent this would be g equals v over 9.81, where v represents the velocity of an object and g is the amount of g-force on the object. The term sound barrier is used to describe the maximum speed at which sound can travel in a medium. As an object moves along, it creates sound waves that radiate away from the object at a speed of 331.3 meters per second in dry air. As the object accelerates towards the speed of sound, the sound waves in front of the object begin to pile up on top of each other as they can no longer move away from the object trading them fast enough, forming a sound cone. The pressure waves bunch up, creating an invisible pressure barrier in front of the plane as it approaches Mach 1. This buildup of pressure in front of the plane creates a much larger force than usual in front of the aircraft. This creates a noticeable increase in aerodynamic drag on the plane, leading to the term breaking the sound barrier as the plane passes through this point. A sonic boom is created by the sound waves of an object traveling faster than the speed of sound. The boom itself, similar to thunder, is a sound created due to the shock waves that form. For an observer standing on the ground, the sonic boom is the sudden onset of pressure after the build-up by the shock wave, and appears like one boom. However, the aircraft is making these booms periodically as the pressure becomes built up and is released. Sonic booms reach the ground between 1 and 60 seconds after the aircraft flies overhead, depending on the height of the aircraft. The strongest sonic boom ever recorded had a pressure of over 144 pounds per square foot and was recorded by an F-4 fighter. When one pictures an aircraft traveling at supersonic speeds, a picture of a vapor cone around the aircraft's fuselage often comes to mind. The cloud created around an aircraft when passing the sound barrier, contradictory to popular belief, is not a shock wave and is instead water vapor in the air condensing due to a drop in temperature. Water vapor is everywhere in the air and only turns into clouds when the air is too saturated to absorb any more moisture. The maximum amount of water in that the atmosphere can hold at 30 degrees Celsius is 30 grams per meter cubed, while the maximum at 0 degrees Celsius is only 5 grams per meter cubed. Therefore, colder air can hold far less moisture. The water vapor cones that form around planes traveling at supersonic speeds are due to the water condensing as a result of a drop in temperature past the maximum amount that the air can hold, creating vapor. Furthermore, shock waves cause an increase in pressure, which results in an increase in temperature, not a decrease, which is why what we are seeing is not a shock wave. The increase in temperature resulting from the formation of vapor cones is a result of the decrease in pressure behind the convex of a plane wing or fuselage. The expansion of air behind the convex of a plane wing results in a drop in pressure and therefore a drop in temperature past the maximum air moisture holding capacity at that temperature. This is why vapor cones always form behind plane wings or cockpits. The moisture cones usually fade in and out of view as the plane flies through zones of higher and lower moisture levels. This effect is not limited to supersonic planes and can in fact be witnessed on planes flying well below the sound barrier. I saw the effect take place on the wing of our plane as we left Toronto on our school trip to BC. While many planes could reach speeds well above the sound barrier by the 1960s, supersonic commercial flight was still something only seen in science fiction and dreamt about by aviation enthusiasts. This dream would become a reality on January 21, 1976 at the unveiling of the iconic Concorde. The plane was an engineering marvel able to halve flight times between New York and London from over 7 hours to just 3.5. The plane would fly over 2,000 kilometers per hour, faster than the speed at which the Earth spins at, meaning that passengers would leave New York and arrive in London before they took off. The plane also flew so high that you could see the curve of the Earth. The days of supersonic commercial flight would come to an end just decades after it was first unveiled, not due to a massive failure, but instead many factors that led to its decline and eventual cancellation. In July of 2000, a Concorde punctured a tire during takeoff, resulting in the deaths of 113 people. The problem was specific to Concorde tires, resulting in all Concordes being grounded until November 2001. By the time the plane was back flying, the airline industry was still plummeting in the aftermath of September 11th, leading to a huge decline in air travel. The huge amounts of noise from the sonic boom created when the planes traveled above the speed of sound meant that the Concorde was limited to flying over the ocean, limiting the routes it was able to fly. Many had environmental concerns about supersonic flight over the damage that the planes were doing to the ozone layer due to the very high altitudes that the aircraft would fly at. The plane was also limited by the amount of fuel that it could carry to only being able to fly transatlantic flights. The huge amount of fuel that it did burn meant that the cost of operations were extremely high. All of these factors led to the Concorde's final flight on November 26, 2003, only 34 years after the plane was first introduced and 27 years after its first commercial flight. Hopefully this video has given you a deeper understanding of the complex history of supersonic flight, as well as what the speed of sound can tell us about how particles move and the ways in which properties of a material affect the speed that sound travels through it.